Hi, and thank you so much for having me here today. It's really a great opportunity for me to talk about my research and for me also to reach out to you and describe what I'm doing. And I'm so happy to be a part of this. So today I'm going to talk about how superphysical systems may or may not be in our society. And so let's see if we can get a start here. Okay, so me who is presenting, my name is Håkansson, and I'm professor in computer science. And as Jonathan just said, I've been around for a long time, and it's many more years, over 25 years now. And some tells me that you must be as old as AI. And well, we may think so, but that's not really true. I'm just coming in a start of an AI winter, actually, when nobody wanted to work with AI. But I thought it was a great thing to do, and I couldn't stop doing what I'm doing at the point and what I'm doing right now. So I just continued. And that was good because now it's a really hot and really interesting topic. So the only thing that changed in my area is that I moved from expert systems to knowledge-based systems to now cyber-physical systems. And I will tell you more about it during the talk today. But when we look at cyber-physical systems, we can look upon them as cars and self-driving cars. So I have a question here, AI in cyber-physical systems, when, parentheses, can fully autonomous cyber-physical systems in society be achieved? Or can full autonomous cyber-physical systems in society be achieved at all? So that is what I'm going to talk about. Before doing that, I just want to mention a little bit of what I've been doing. And so I'm now presenting from Tromsø, and you can see the northern light behind me. And we have a lot of that right now. And it's actually already dark here, even though it's only 4 o'clock in the afternoon. So we can actually see that right now. So we are all the way up in the Arctic Circle when it comes to Tromsø. And I am a professor there in computer science with focus on AI. But as you can see, I'm also in Trondheim, and I'm working there part-time, as well as I'm at the Royal Institute of Technology, KTH, in Sweden. So I also have a part-time there. Beside that, I'm a director of a KES group that is working with AI, and I'm also editor-in-chief for a new journal called Nordic Machine Intelligence Journal in Norway. And I have been around for a long time, meaning that I moved around between different things, but something I never really moved from is reasoning strategies and how to reason among things and within things, and how to negotiate between things so you can create a better environment. And as I said, I went from expert systems, which have knowledge inside them and also are reasoning. But nowadays, there aren't that many working maybe in expert systems, but they are still around, because even though we don't call them expert systems, there are systems that we can find that are similar to that in like agent systems, but also in cyber-physical systems. So I'm kind of around in that area. And I'm also working a lot with visualization and graphic representation, because my idea have always been that we create programs, but we really don't remember what we have done, or we even lose a sight of what we want the system to do and what it's really doing in the end. It's really hard to explain what's going on. And that's why it's so important that we can show this when it comes to some physical system, what it can do, and so on. So that is a part of it. So working with heterogeneous data from environment and also real-time data is something that is utterly necessary to do cyber-physical systems in societies. So what are cyber-physical systems? Well, if we look at, we talk about the cars, of course, but if we look at from the beginning, a cyber-physical system doesn't have to have any intelligence from the beginning. It was just discussed about how things could actually have several different components, algorithms, and networks integrated in one system. And if we have that tightly integration, then we have a cyber-physical system. And some tells me that, well, it doesn't work without an AI. Well, that's true if we really want to have a smart cyber-physical system. But that doesn't mean that all the cyber-physical systems have an AI technology within them. But when I work with them, I always talk about them as having intelligence included in it. So cyber-physical system is integration of these parts. And it has a feedback system, so we can record signals from the environment, we collect data. And when we get that to the system, we can make decisions, and we can also send the data and use the decisions to use the sensors and move in a way that it behaves intelligently. So if we think about a car, if we have record signals from the traffic, we can make decisions in where we are for the moment in the traffic. And we can then get the cyber-physical system to work accordingly to the traffic. And this is a highly dynamic environment, which makes it really tricky. And we need to have the 3 C's, as we will call them: communication, controlling, and computing. And these are important parts in a cyber-physical system, as well as a decision-making part, so we can really work with the data we have. We also have elements that are in a network. So the network is a part of the cyber-physical system. And if you look at the image here, you can see we have a cyberspace where we also put a lot of data. You may not know, but for instance, Tesla, when they are working in the environment, they also push data up to the cyber-physical space or the cyberspace, so it can share the data with the other cars that are in the traffic, so they know, or those that are there can work with the data which my car, my Tesla, would have sent to the cyberspace. With that data we have in the cyberspace, we can work with the actuation information, so we can do things in the environment, in the physical environment. And when we have done something and we have sent something, we can also send the data up to the cyberspace. So it goes in a circle, and that is a circle that is very important, that we don't miss data somewhere on the way, because losing data would be fatal for the cars in a traffic, for instance. I talk a lot about cars, but cyber-physical systems we can find everywhere. And we talk about systems that are autonomous, because we want them to be able to work without a human intervention. So we don't want humans to be in a part of everything. We want them to be able to work by themselves. So the autonomous systems, when I talk about cars, it's only one thing. Drones is another thing. And drones have become a really big, important part when it comes to finding problems in, for instance, telephone lines, electric lines, forests, if there is a fire, and so on and so forth. So we use them for surveillance, but we also use them for controlling how things are working in the society. We also work with them when it comes to smart grids and how we can improve them. And since the drones are, for instance, a part of surveillance, they can also provide data so we can build even better and smarter grids based on the data we get in to the system. We have monitoring when it comes to medical and healthcare, and we can monitor the patients to get and give a better healthcare. And we can do that also remotely with the help of the machines and with AI. So we can create smart systems that are providing much better healthcare on a distance, but also locally, of course. Industry. I think many have heard about Industry 4.0, and cyber-physical systems, they are a part of that. And they are the robots that are working 24/7, as we would say that, without any stop. So we can actually have good robots that are working autonomous with human or without human being a part of it. Mostly we talk about without them. The system needs to cooperate. So cooperation between the system is very, very important. If we want to have them in a traffic, or if we want to have them in the Industry 4.0, or a building, or doing a better or work with energy, then we have to have systems that can cooperate. So it means that we not only have one cyber-physical system, we have several cyber-physical systems working together, like a multi-agent systems. We can have a swarm of cyber-physical systems. For instance, drones have been shown to work well. I don't know if you have seen the Olympic game in Seoul. They use drones to show a very nice figures and so on in the air. Those drones had lights, and with the lights and with a very nice design, they could fly and they could form these very nice figures. But that is just one part of what you can do with cyber-physical systems. But having many of them together, for instance, in the Industry 4.0 or traffic, that is where we will see them very often. Monitoring and controlling, I said already, but we want that because we want to support the humans and strengthen their capability to work with healthcare, but also to prevent disasters and so on. If we can find a fire very fast with using a cyber-physical system, we could actually work and they can deliver data which we can use to provide better help. And these can operate in dangerous and in inaccessible environments. I talk about fire, but we also have avalanches, and we have high waves in a storm of water and so on. The drones doesn't work with storms, but we have cyber-physical systems that are boats. So we can use instead when we need it. And these can work, the cyber-physical systems together can be distributed so they can work together to solve a problem, which is a great thing when we have a catastrophe like this. If you look at the picture up to the right, there we have several different cyber-physical systems. So there is a robot that looks like a man almost. It is a car, it is ambulances, that is other robots that can work in if something have happened to a building, for instance. And we have the drones, flying vehicles and so on. So together with that, we can make a smart environment with many smart and efficient cyber-physical systems that are working together, and that requires decision-making and negotiation. So that gives you maybe a little bit of an idea of what cyber-physical systems are and what we can use them for. So when we talk about the cyber-physical system and the benefits, there is a lot of problems that we need to deal with. Because we have the decision-making in a cyber-physical system that is within one, but also between several systems. And to make decision autonomously or to work in an environment by themselves means that they need to know the goal. They need to know what they are supposed to do in the setting. We have several tasks that they need to carry out, and they need to know which drone or which cyber-physical system that is going to carry out the task. We don't want them to do the very same task, all of them at the same time. We want to spread it out, and we want to make them work together. And we have an environment where the cyber-physical systems are working with or without humans. For the moment, we have cyber-physical systems that do not work without humans. We have a human, a part of the cyber-physical system. And, but we don't want them to be a part of it all the time, because if we require a human to always be around and tell the cyber-physical system what to do, then we really limit the possibility of the cyber-physical system. So we only want them to operate when and only if needed. So it's only if and when needed. So these needs to be able to work as autonomous as possible. And to do that, they need to learn from the environment, and they need to learn from how the human want the cyber-physical system to work, and they need to have a decision-making that is valid and trustworthy and can do that decision-making in real time, because a catastrophe happens now and at a certain time, and then the cyber-physical needed to be ready for that disaster. So, but even small things can be very difficult. If we look at the cyber-physical system that are working in a traffic, we have signs. And those signs means that there is a problem in the road. And how can the cyber-physical system that is totally autonomous read those signs and understand what's going on? And how do we communicate those signs to the cyber-physical systems? Cyber-physical system can use, of course, AI to recognize the signs, so they know that, for instance, the first one means that we have a narrowed road coming up, and we can tell that in beforehand what we have at hand. But if we have a traffic there, how could they actually know that there is other cars there? And what does that mean? And how narrowed will it be? And is it enough to make the cyber-physical system car to pass? For the moment, the cyber-physical systems like autonomous cars, they want to have a particular space around the car, otherwise they won't pass. So a narrowed sign like this, if it's too narrowed, the car may just refuse to pass. So that's something we need to look at. And also, if we have pedestrians together with the traffic and external vehicles and traffic sign, we can actually create deadlocks, which we certainly don't want when we have these systems in traffic and they are working totally by themselves. So what is really needed and what must be done to start accepting the cyber-physical systems that are autonomous in society and in cities? Well, first of all, look at what is autonomous and what do we really mean by that? There are a number of different levels of autonomous. We have from 0, which we mean no autonomous at all, it's no automation, up to level 5, there is full automation. And then we have several different levels. And when we talk about autonomous cars, we usually want to talk about full automation. And that is when no human driver is required or is even allowed maybe to steer or take over the wheel. We don't want them to do that. But where are we today? Do we have full automation? I would say that we maybe have partial automation, which is level 2. That must be a driver is alert when the vehicle needs the driver to be alert. So it actually is a part of helping the car to move or to drive in a society. And if we look at most of the cars today, that those require that the driver is awake and alert, and that the driver needs to be able to step in from time to time to make sure that the driver does not sleep. So that is about where we are. We may be able to go to conditional automation, where we have a driver that is always ready to take over. But as far as I know, most of the cars require the driver to at least touch the wheel or move it a little bit so the car does not turn the autonomous self-driving mode off, so it's still working. So the level of autonomous is actually many, but we are talking about level 5, and that is, do we or can we really have a full automation when it comes to cars? Well, we think so, our group thinks so, that we should be able to do that at some point. And what does that mean? Well, we need to have cars that can adapt to the environment. When it comes to roads out in the countryside, we can drive far. But when it comes to cars, when we have environments like heavy traffic in cities, it's another deal. But you see up here to the right, you can see a fully autonomous car where the driver doesn't touch the wheel at all, and it's driving in a city. So it is possible, even though we still cannot maybe trust them totally yet, but they need to be able to adapt to the environment. Another thing is that they need to have a complex decision-making to adjust the behavior. Right now, you can see the car is only moving forward, and now the driver touched the wheel. So when it comes to forward driving in a straight line, that works rather well. But as soon as it is coming to a curve or we want to make a turn, then it's different. And we need to be able to negotiate between the cars that are in a traffic light. And if we have a green light, we have cars that are coming towards us. And if we want to make a left turn or right turn where we need to pass those cars, then the cars need to negotiate so we can actually drive there. So they need to tell which one is allowed to go first, and so on and so forth. So they need to make sort of a list or a queue who will be able to move or turn. So that's one thing. Another thing is that we need to have a trustworthy automated decision making. So we need to trust that when the car is out in the traffic, it will always behave in the right way. So it is not allowed to hit anyone. It must always be safe, and we must always be able to trust it, so we don't have to take the wheel when the car is not knowing what to do. That means that the car may have to stop before doing anything else. So there will be a lot of car stops and then decide what to do, which will slow down the traffic. But I would say in the beginning, that might be the only way to do it from the beginning. Another thing is that the car needs to have a self-management and self-control part. And that means that it must have a possibility to know when it can do something, when maybe a battery is ending, where to go, and so on and so forth. So it needs to be able to figure out the whole situation from when it starts to move around in a traffic until it ends. And that an end is when they don't work any longer. So we should be able to trust them. As soon as they get into the traffic, they should handle the traffic. So they need to be able to control that. We also want them to be giving us an optimal way through a traffic. We don't want them to go around and around and around and not come to the goal. We want them to have a clear goal and go directly to the goal. So they should be able to optimize the way through the traffic. At the same time, an autonomous car needs to fuel and probably its battery. So they need to figure out also when it needs to be charged and where it should go to get this charge. So it's a lot of things that is connected to these systems that is not maybe totally obvious. And also, if a car breaks down, how should it be able to heal itself, or how can it mend the problem? If it's a software, it's easier. If it's a physical part, it's more problematic. A software, we can maybe have a self-healing where a bug could be fixed, or we can even have a software that can be sent between the cars if there's some that has been really problematic, even though that requires a lot of security aspects. So we don't want the cars to be updated during driving. We want them to be updating when it's standing still. We don't want to create more problems. We want to make it easier for the cars to be able to do something. So to be able to do that, we need to know a lot about the cars. And if we look at the Tesla, I don't say that we have to have a Tesla. It could be a Mercedes, it could be an Audi, it could be a Polestar, it could be any of those car brands. But I just take this as an example. So what do we have in the cars? Well, we have the cameras, we have a radar, we have sensors that we can work with, and we have a supercomputer, or at least a computer that is computing the car and all the data which we get in from the cameras and from the radar and so on. So with that data, we get into the car and we need to compute with what we have. If you look all the way to the right, you can see how far we can see with the cameras. So we have different distances depending on which of the sensor or device we use to collect data. Some we have long distances, well, rather long distances, and some of them are very short distances. This makes it very tricky to see some objects that have no solid parts, like a bicycle is very hard to see, or a reindeer with very small legs is also hard to see. So it is difficult to see objects that doesn't have a really heavy solid part connected to it. So to be able then to move in traffic, you need to be rather close to the other cars. The question is, how close do you want it to be? And the negotiation between the cars can actually be done with a bigger distance. But if we get the cameras and we want to use the data from the cameras, we actually shrink this space a lot. So we can't really use a long distance when we want to use the camera data. And that is something that we also are working with. So we need to figure out the data we have, what we can do with it, and also negotiate between the cars. The problem also we have here, we don't want the cars to have too heavy computation, because too heavy computation means that instead of doing something in action in the traffic, they may only stand still and do nothing in the traffic. So that is also something to think about. So what we are working with in our group is to work with the environments that we have a lot of data in, and we have also many agents in that environment. And the environment is built with what we call solid blocks, like buildings, but we also have dynamic blocks, like other cars. But there are also other dynamic blocks, and that are pedestrians. So with the pedestrians and cars and other moving vehicles, we have to encounter them as different dynamic parts. Some move fast and some move slow, and we also need to know the speed so we can calculate fast with how we can behave in that environment. So we work with also collision avoidance. So we want to avoid collision with calculating other parts, cyber-physical systems and pedestrians and so on, their speed as well as our own speed. So we need to know the speed. Another thing that is required when it comes to the environment is 5G, the 5th generation networks. We need to work with as close real-time data as possible. We don't want to have any latency in that. So we need to have many antennas that can provide us with data and also provide it with data very fast. And we write big data because we think that we will probably have a lot of data moving around in the environment. But what happens with big data, and we want to calculate fast, is that it's contradictory, because it's a contradiction between how much data you can use and how fast you can compute it. So that is problematic. Also, preferences from humans. Do we want to have autonomous cars doing whatever they like, or do we also want them to have human preferences included? Well, in the autonomous cars, we would like to stay out of the human preferences. But if a human is going to be in the car, the humans want to have their preferences in the system. So of course we need to take care of that. Human may want to go slow. They maybe want to have a smooth stop. They may want to have a fast car, and so on and so forth. And we cannot do everything, but we can do something. And the humans are very, very important in this part. And we have something we call pull-push technology. So we pull data and we push data between the different devices. So that is some of the data we need to use. And what are we doing then? Well, we try to have a robust, autonomous, or automated decision making. So we want to have it in a robust way, meaning that the decision making needs to be with analyzing the data we have, and we should have the options that are possible to carry out in the environment, not options that we can give when we are analyzing data. We want to have the options that are important to us, and we can do something with that in the situation we are at for the moment. So it's very important that the data is the decision making is trustworthy, the conclusions are trustworthy, and the system behaves in a robust way. So we can always trust that the conclusion we get from the decision making is also important and something we can use. The conclusions we use for negotiation, but also predicting when we need services for the cars and so on. So negotiation I talked about already, but we can tell where we are going, what we want to do, what the speed is, and so on and so forth. So we can provide a lot of data. But that's important that we only provide the data to the traffic that is interested in it. We don't want to give it to everybody that is out in the traffic, only to the cars that could be involved or are involved and will be affected by a cyber physical system moving in the traffic. So the environment we are working with is highly distributed, but they are connected in some way. And we need to have coordination of actions in the environment. And the data is temporarily given, and it's heterogeneous because the different vehicles and different cyber physical systems will give different data because we have different brands and they need to be able to communicate with each other. Latencies and latency sensitive is highly important because we need to be able to react as soon as something is going on. If there is a cyber physical system, another vehicle moving towards us, we need to be able to stop, or we need to be able to avoid disaster. So we should be able to actually very slowly avoid by just turning around the car and so on. So that is something we work with right now, is to have a smooth way of handling the traffic. And that means that we don't just stop every time something happens. We try to figure out the best way to surpass each other. So we want to pass each other in a very nice and smooth way. To be able to do this, we have some requirements. The systems need to be adaptable to the dynamic environment. They need to be scalable because we have heavy traffics, and they are something that is really giving a lot of limitations and constraints to our systems. So the system must be handled a large scale environment with a lot of cars or other vehicles in the environment. It must be robust and responsive. We need to have fully control of the system so we know what's going on. I don't mean that we are driving when I say fully controlled. I mean that when the cars are doing something, all the cyber physical systems should be able to communicate to the humans of what's going on in the traffic and how they are reasoning with the data. And they should also show why they come up with a certain conclusions. So they need to be able to handle the environment in that way. They need to be resilient. We need to be able to trust the cyber physical system to always work We should never be afraid that something is going to malfunction or stop or make a disaster or something. We would like them to be have resilient systems, but also create a safe and secure environment. And as you probably know already, this is not easy. How can we really ensure that our system is fully trustworthy and that they have a robust system and they have a robust decision making underneath? But that is important if we're going to allow these systems in the traffic. Another thing is that we don't want to create the cars over and over again. We want them to have a usable and reusable feature so we can reuse them in many ways. So we have a virtual infrastructure to work with that. So we are creating an infrastructure over the traffic, and we put the different parts in the environment, and then we work with the data. And you can see the picture here. It's different cyber physical systems, but that is just a simulation of the data we need to get in, and also how to work with the data in our society and in the environment. So we have robots, we have embedded chips, we have smart grids, we have vehicles, and we have also other devices that humans are wearing. That is a ring, but we also have other things like cell phones and so on that tells where the pedestrians are. Often the pedestrians have information about where they are in a situation, because most of the people already have a cell phone or a ring or a Fitbit or something. Not everybody, of course, but with this data, we can do much more. That doesn't mean that we shall not look at pedestrians that does not have any of those devices, but for those we can use cameras. So with the cameras, together with the devices that people are wearing, we can actually create this virtual infrastructure with different simulations of different parts. And why we use this is because they provide heterogeneous systems and a simulation with that, because we know that we have a lot of data coming in and we never know how to handle the data. And that's really important, that we have something that could be an intermediate part between the systems, so we can communicate. We shall not have to have standards. I know that Internet of Things community always talk about standards, and of course it is always nice to be able to have standards, but I would say that it can be tricky to have only one standard. And why do I say that? Well, we don't have any standard all the way around the world that is the same. We drive on different sides of the road. We have different measurements. We have different ways of handling our daily society. So of course this will be different, but we don't want to have cars that can only operate in a certain environment. We want them to have possibility to move from one environment to another without changing everything. So this is my last slide before questions. So I talked about this already, but I would like to come back to the question, when, or would I say, can we have fully autonomous cyber-physical system in society? So can we, or when can we have that? Well, there is a lot of things that we still need to work with to be able to make that happen. So with that said, I thank you all for listening to me and for what we are doing at our lab. And if you have any questions, I'm happy to answer them.
Thank you, Anne, for a fantastic talk once again. If anyone has any questions, if you please put them into the Q&A. And hopefully while we'll wait on it, we'll get some questions coming in shortly. There is another option. If you wish, you could put your hand up and I can unmute you to ask a question live. So
when they are thinking, I can also mention if somebody is interested in the lab or collaborate or work with us, I'm happy to receive their emails, and we can be in contact via emails and maybe do something together.
Oh, that'd be great. We've just had someone thank you for your presentation. Email. I'm still waiting to see if we may not get any questions because it was a very thorough talk, and I'd like to ask a question, but I don't think. Oh, I've got one question. I'd like to, I'd like to ask you about the work you've done. Do your work with collaborative communication work between vehicles? So the work is.
Yes. So first off, we started off with decision making inside cyber-physical systems. So we had several different. So we built like a multi-agent system. So we had several different cyber-physical systems handling themselves. And the next step was to start to make them collaborate with each other. Because, for instance, in an industry or a traffic, we have different rules. And we wanted them to be able to negotiate and tell where they are going, what they have in mind and what they are doing, and also how fast they go and so on. And that is to avoid collision. And we are still in the phase where they do collaborate and they do communicate, but as soon as something comes up that is a little bit sudden, instead of smoothly go around each other and communicate, they stop first and then they move. So it looks like an old simulation, sorry, for SimCity or so, when everything stopped and then started to move again. And we don't want that. We are now in the phase of working with reasoning, where we can use uncertainty with logic. So we have uncertainty and logic, and we try to make them move as smoothly as possible. So that's where we are right now.
That's great. We've got another questions coming from Gloria Wren. Thank you for an interesting presentation. Is there any literature on the characteristics of decision environments that are better suited to humans versus autonomous?
I don't know if it's directly towards either or, but I do know we have literature, and I have written about this volatile infrastructure and so on. So there you can find something, but it's not like it's only directed to either humans or autonomous system. It's more like how to have them together in the environment. So no, for the moment, I don't know anything about it. At the same time, I would say that surprisingly, that I haven't seen a lot about virtual infrastructure in the first place, which is really interesting. And I think that we need to do much more here, because we need to work with the digital side of what we are doing right now in a virtual environment, so or in infrastructure. So we need to have a layer of a virtual infrastructure together as a part of the other commonly described infrastructure, like transport and healthcare and buildings and energy and so on. So, yeah.
We've had another question from Professor Howlett. What do you think about the computation in the cloud versus at the edge for the AI components of the CPS?
Yeah, thank you so much for a very good question also, and thank you all so much for all very good questions. And well, when it comes to cloud and have a real-time computation, I get a little bit sweaty, I would say, because we don't want to store a lot in the clouds if we want to get access to it very fast. So edge, or what we also call fogs, I think storing and working with things in the edge is much more important. And I would also say, and also tell you, that we do work a little bit with the edge too. So we do some computing in the edge, but the question is then comes to the communication between the parts, because a cloud could communicate between the cars easier than if we had the edges communicating with edges. So, and again, we don't want to have a lot of computation in the edges either. So it's some beneficial to have it in the edge, but it's also some benefits of having in the clouds. So I would say that if we could divide that in a very good way, in a balanced way, I think that would be the best. So we do what we do the best in the edges and do the computation there when we need it, and the clouds when we need that.
We've got 4 more questions, if that's okay, Anne.
Yep.
We've got one from Victoria. How do you think the cyber attack on the AV will impact the public's trust stroke uptake of the...
Yeah, oh my God. Oh gosh. Yeah, well, when we have the first time something happens, that will really affect the whole environment, and we will, of course, have a discussion of the how to handle security, how to handle cyber attacks, how to handle traffics and so on. But I do think we will also come back again and recover from it. But unfortunately, cyber attacks are really something that is tricky for us. And therefore, it's important to keep in mind what shall we communicate, what can we communicate, and what shall we not try to make the other cars do. So if we can have most of the decision making in the cars, but only tell where they are going, but not just trust it, but also be aware using the cameras and sensors, also see if something is going on, we could still act and react. So we just not want to let them just work in the traffic and give the hackers a possibility to send wrong information to the cars and just act upon it. That was a long answer, I guess.
We've got another question from Wagi Maraji, I think I pronounced that correct. You mentioned that the CPS system should be autonomous, but at the bottom of one of the earlier slides, you also said the humans should be involved.
Yes. Okay, yeah. So the thing is that for the moment, if we look at what we have, is that the humans are very much involved. And I know that there is research saying that if we don't have humans involved in the cars, that if they would be fully autonomous, the cars would make less problems. I don't know if that is true or not. But what I really want the cyber-physical systems to do is to work autonomous, at the same time give us humans information of what's going on. So we would like to be informed, but not maybe intervene so we will make a problem rather than just follow what the cars are doing. So what I would like to say that humans should be informed, but not maybe be the ones that take the wheel over and then do something. And again, I just said to my students today, would you trust your 2-year-old boy in an autonomous car? I don't know. I wouldn't do that, not for the moment. But and I also heard somebody saying, well, if we are in trouble, there is only an on-off button that you can use. But I say that if things are in the clouds, which are the buttons you are going to turn off? We can't turn them off any longer. Everything is digitally. So it's really not a possibility any longer because we don't have any control over the systems any longer, unfortunately. So if we can make them autonomous, I would say that if we can make them trustworthy, that would be really, really good.
Okay, excellent. Just a couple more questions. Samara, thank you for the talk. What happens in the case of casualty crash? Who will take responsibility for it within an accident?
Yeah, well, the thing is that for the moment they say that the car manufacturing companies are the ones who are taking responsibility for something that have happened with their cars. But every time I read about that, it's always somebody who did something wrong. Somebody was watching a game, or somebody was sleeping, or somebody did something else. So it seems like even though they say that they're responsible, I haven't really seen the responsibilities, if I could say that. But I would say it's very important that still that the manufacturing companies know what they are doing, and they need to be responsible for creating these systems. And therefore, they also need to be responsible if something happens. So if the human should not be the one who will make or will be able to make a problem or infer something that they shouldn't be doing. So, yeah.
Thank you. The last question from Panagiotis is, do you think that more realistically applied scenarios should be applied in the terms of digital forensics in terms of AI-enabled healthcare systems?
Oh my God, that was a very, very good question. And I think it's possible to make more realistic scenarios. And I do think that we can also use this for digital forensics. And one of the things is that these cars always tells where they are and what they are doing. So we can harvest more data from them. And so that is one thing. And also now we talk about cars, but also when it comes to robots and robotics in the healthcare, we could actually also get data from them and harvest data. And it's easier to see when something goes wrong. So I think it's possible to get more and do more because we can harvest data more now than we could do earlier. And that could be done and used for many different scenarios. So, but again, we have to try this out. We need to try it many times to really be sure that something is working as we want them to do, as we want them to work.
Thank you. I've had one more question come in, and that'll be the last question. It's what is the state of the what is the state of performance of state of reinforcement learning algorithms for training autonomous vehicle decision taking used in real world, or are these learning algorithms only limited to games?
Okay, that was a long question.
I know.
But I can tell that we are actually using reinforcement learning right now for our agents. So for each and every one, we use that. And we have a rather good result there. So we are actually happy when each agent is moving in an industry 4.0, for instance. So we can trust the agent that separately. But the problem is more like when we negotiate between the different cyber-physical systems, and how we also work with robust reasoning, actually. So we have not been able to really have a good result yet. But what we are doing is that we try to apply different strategies. So we not only have one strategy, we are combining different strategies. So we are trying to make a more robust environment for the systems, as well as in the systems and between the systems. So what we are trying to do is that we work with uncertainty in the reasoning. And with that, we hope, because we don't have the results yet, not good results, we just started and we have done some simulations. But the thing is that we try to work with trustworthy intervals that we can actually allow the cyber-physical systems to work within. So for instance, in a space that have like a certain distance between the different cars, or in a road, how much can we actually tell the system to narrow it a little bit before it becomes problematic. So that's something we have done, because if you remember, I said the signs that goes together, and that will actually tell the systems to stop and make a deadlock. But with our systems that we have a smooth bypass, but we don't have, we can't say yet that they are trustworthy enough. So we can't say that we have a robust system for the moment. So we can't really trust the environment. But if we can have more elaboration, more simulations, and we know how much we can compute in the cyber-physical systems, as well as between, coming back to the edges and clouds, and how much we can allow, then we know much more of what we can do. I don't know if that was the answer to the whole question, because it was a long, but a short answer, yes, we use reinforcement learning. The long answer is that we combine it also with robust decision making, which is making analysis of the data that we have.
Thank you, Anne. I think that's it from everyone. Anne, thank you once again for being our first speaker, our first KES Talks. I'd like to thank everyone for attending and asking some very interesting questions. But again, once again, Anne, thank you very much. And I'd like to bring this session to an end, and we'll say good evening and goodbye.
Yeah, and thank you so much for having me today. And thank you all for great questions. I really enjoyed this opportunity to talk to everybody and tell what we have been doing. So thank you so much.